Okay, good afternoon, UKStratCom. It's a pleasure to be here to tell you about rocket science, or perhaps it's not rocket science. As you can see from the subtitle there, the idea is, can we get across the basic ideas without the maths? Because that's really what makes rocket science difficult.
What do you do?
Why, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science, is it?
And that, of course, is the perception. Rocket science must be difficult. What I'm talking about here is not rocket technology or rocket engineering. I'm not talking about how to build rockets. I'm talking about how we get around the solar system using rockets to take us from one orbit to another. So I'll be looking at what rockets do. I'll be looking at orbits and how we get from A to B, using as an example how we get from Earth to Mars, and also how we use other planets to give us an assist in getting from A to B. And I'll finish with these rather odd parking places that we can use in the solar system, the so-called Lagrange points. So firstly, what do rockets actually do? Well, if you ask most people, especially Joe Bloggs in the street, what's the primary function of a rocket? Well, a lot of people will say, well, the purpose of a rocket is simply to lift things above the Earth's atmosphere. Well, yes, sort of. But bear in mind, objects like the International Space Station or the Hubble Space Telescope, they're actually still in the Earth's atmosphere. It's simply rather thin up there at an altitude of 400 or 500 or 600 kilometers. So to put an object into Earth orbit, what we actually need is not vertical height as such. What we need is horizontal speed. So yes, getting as high as possible to reduce atmospheric drag is definitely a good idea, but it's not strictly necessary. And this was known back in Isaac Newton's day. So for more than 300 years, we've appreciated that horizontal velocity is key. His idea was this thought experiment. What if you were to place a cannon on top of a mountain top and fire the cannonball sideways? Well, it's the horizontal speed that dictates what's going to happen. If you haven't got enough horizontal speed, the cannonball will drop to the ground marked A. If it's going a little bit faster, it'll drop to the ground at the position marked B. And if you go fast enough, then it'll go all the way around the Earth and it will be in orbit, as indicated by the other dotted lines. Newton also realized that the stronger the Earth's gravity, the faster the cannonball needs to go to be in orbit. And that particular observation is key to what I'm going to be saying in this particular presentation. The stronger the gravitational force, the faster you have to go to stay in orbit. Let's remind ourselves what a rocket launch looks like. Yes, initially the rocket moves vertically upwards, but it's not too long before the rocket starts to tilt over to one side to increase its horizontal speed. And the angle you can see here is not simply a trick of perspective of where the camera was placed. This is a genuine tilt in order to get the horizontal speed as high as possible. So the rocket, in a sense, is twofold. Its job is to get the object high, and in principle, it's to get the horizontal speed as high as possible to put the object into orbit. If you don't have any horizontal velocity, for instance, the Blue Origin New Shepard spacecraft, it technically went into space because it achieved an altitude of 100 kilometers, but basically it went vertically up. It gave no horizontal velocity, and therefore, once the fuel was used up, it came vertically down again. So that 10-minute flight was what happens if you have no horizontal speed. You can technically go into space, but you can't go into orbit. So let's have a think about the nature of orbits. Now, an orbit is simply the path of an object affected by only gravity. And we tend to think of orbits as those closed paths, circles or ellipses of planets going around the sun, or perhaps moons in orbit around their planets. I'll say right at the end of this talk about something about the fact that orbits don't have to be closed shapes. But when we're looking at planets and moons and satellites around the Earth, then we're talking about circles and ellipses. Kepler was the first to observe that the planets orbit the sun in ellipses, and Isaac Newton figured out why that was. It was a manifestation of his law of universal gravitation. And Newton figured out that objects moving in a gravitational field will follow one of these orbits: a circle, an ellipse, a parabola, or a hyperbola. And each of these shapes are called conic sections because each of these shapes is the result of taking a cone, and if you slice it horizontally you get a circle. If you slice it at a jaunty angle you get an ellipse, shown in green. If you slice it at an angle parallel to one of the sides of the cone you get a parabola, and if you slice it at a larger angle you'll get a hyperbola. So regardless of the names of these things, they are all just sections of a cone, and Newton figured out the maths of why this was. If we look at all those shapes together and imagine a circle or an elliptical orbit around the sun, shown in yellow there, you see they all look very similar when they're at their closest to the sun, but very different when they're further away. And planets followed these closed shapes, these elliptical shapes. A circle is just a special case of an ellipse, which is as wide as it is high, effectively. But a comet falling into the solar system from way out in the Oort cloud. The Oort cloud is a huge cloud of icy particles a long way from the sun. Parts of the Oort cloud might be, for instance, halfway between our sun and the nearest stars. Any object falling in from the Oort cloud should follow a parabolic path, and that's what we see for various comets as they pass by the Earth. If an object enters the solar system at speed rather than dropping in starting at 0 speed from the Oort cloud, if an object comes into the solar system at speed, then it will follow a hyperbolic orbit. And we've seen that happen once or twice. For instance, back in 2017, the object this rock came into the solar system in 2017, and it followed a path shown by the white line there. It came quite close to the sun, within the orbit of Mercury. It's at a little bit of a jaunty angle, so it was in no danger of passing particularly close to any of the planets, but it came in at speed, gained speed as it passed the sun, and lost a bit of speed as it went out of the solar system, but essentially will leave the solar system at the same speed that it came in. And we can verify by plotting its position as a function of time that it was indeed on a so-called hyperbolic orbit. Now, regarding how objects move, the size of an orbit is intimately related to the orbital period. Remember what Newton said about firing cannonballs from a cannon on top of a mountain? It's not actually the height of the mountain that matters, it's how strong is the gravity in which we're trying to make an orbit. So here's a couple of hypothetical objects orbiting the sun. Let's say they're planets. The green planet is closer to the sun, so its gravitational pull from the sun is stronger. And so the planet moves faster to stay in orbit. By comparison, the red planet is further from the sun, so the gravitational pull from the sun is weaker, and so the planet moves more slowly to stay in orbit. So the length of time it takes to do one complete revolution of the sun, its year, will be longer. Let's just run that again to make sure we're perfectly clear what's going on here. The actual speed of the planet is faster. It's not simply that the green planet has less distance to travel. It is moving faster because it's in a stronger gravitational field, being closer to the sun. And that is absolutely key. Newton observed this, and this particular little animation reinforces it because it is key to most of what I'm going to be saying here. Let's see that in action. This is a rather busy animation, but what we're seeing here is an animation of some satellites around the Earth, some in low Earth orbit, such as the Hubble Space Telescope and the International Space Station, but also some other satellites. So we can see that the Hubble Space Telescope takes about 90 minutes to go around the Earth, but more distant objects, such as the GPS or Galileo satellites, will take substantially longer, 12, 13, 14 hours. And right on the outside, geostationary objects at a greater distance will take 24 hours to go around the Earth. So it's exactly the same idea as planets around the Sun. If you're closer to the Earth, you feel a much stronger pull of the Earth, so your orbital speed has to be substantially higher in order to stay in orbit. Again, let me just run that one more time so we can see that. The objects very close to the Earth, it's almost independent of altitude, 200, 300, 400 kilometers. They all have a period of about 90 minutes. Only when we get to things like the GPS and Galileo satellites do we find a distinctly longer period of many, many hours. And the final geostationary orbit right at the outside there is the 24-hour orbit. Now, we can always work out what's going on with two objects. In other words, a satellite going around the Earth, we know exactly how to solve that problem. In physics, we can reduce it to mathematical equations and we can solve those equations. Newton figured it out. A lot of undergraduates at university are doing this all the time. So if it's a satellite around the Earth, or the moon around the Earth, or the Earth around the Sun, we can write down the equations of motion and we can solve them. However, if there are three bodies involved, it's rather embarrassing to admit that we don't actually know how to solve that. In other words, we can't solve the moon going round the Earth and the Earth going round the Sun at the same time. We can do simulations, we can do calculations. So for three objects like shown here, it looks like they're behaving themselves because it looks like they're all following elliptical paths. But actually, if we do the calculations or do the simulations, we find that they are far from elliptical paths. They are following much more complicated paths that are essentially impossible to predict. And that is always the case with three objects. We can do a simulation, we can do the calculation, we can make approximations of how things are going to move when we calculate the gravitational forces between them. But we can only solve exactly an equation when two objects are involved. So quite often we have to make the assumption, if we're talking about, for instance, a satellite around the Earth, we simply have to ignore everything else and just assume that those are the only two objects in the problem we're trying to solve. Let's think about how we use our knowledge of orbits to get around using rockets to change our velocity. If we take one example, for instance, how would we get from Earth to Mars? Here's a section of the Earth orbit shown in blue and the Mars orbit shown in green. There's the Earth at the bottom with a pink object about to leave the Earth. So let's run the animation. There's the object. It's the InSight Explorer on its way to Mars. And you can see that to start with, the object is going a little bit faster than the Earth. It's now moving away from the Sun and slowing down a bit. And as it approaches Mars, notice that Mars is slightly behind it. So Mars is actually catching it up. Mars is going a little bit faster than our spacecraft. Let's just see that animation one more time. The spacecraft is on its way to Mars, having left the Earth. As it approaches Mars, Mars is actually traveling slightly faster than our spacecraft. And that's relevant for what we need to do if we want to actually rendezvous our spacecraft with Mars when we get there. Let's see this scene from directly above rather than perspective. This is a little too complicated. Let's just dim that down a little bit and say, let's assume that we've got a circular orbit for Earth and a circular orbit for Mars. Neither of those statements is strictly true. They are both in ellipses. But let's just keep it simple. And again, I am not attempting to show these to scale. This is purely a cartoon to give us an idea of what's going on. The best way of getting from the Earth to the Mars without, or at least with using the minimum amount of fuel, is the so-called Hohmann transfer. It's a transfer orbit to get us from the orbit of the Earth to the orbit of Mars with the minimum amount of fuel. And the Hohmann transfer looks like that blue ellipse there. Let me just temporarily take the other two circles away. So you can see the blue circuit there is an elliptical orbit around the Sun, which just touches the orbit of the Earth at its closest point to the Sun, and it just touches the orbit of Mars at its most distant point from the Sun. And if we think about how we're going to go from the Earth into that blue orbit, we need to go a little bit faster than the Earth is going. So we have to give our spacecraft a kick. We have to give it a so-called delta V, a change in its velocity. We have to accelerate the spacecraft, which we normally do with a rocket engine. So our rocket is not only going to get our spacecraft above the Earth's atmosphere, it's going to give us a horizontal kick. It's going to accelerate it for probably a few minutes to give it a change of velocity that's sufficient to go from the Earth orbit, the green curve, to the blue orbit, the Hohmann transfer. And remember what I said, when we get to Mars, Mars is actually going faster than we are when we reach Mars. So when we arrive at Mars, if we want a rendezvous, we have to accelerate the spacecraft a little bit more to catch up with Mars, which is going faster than we are. So we need to fire a rocket engine to leave Earth orbit, and we need to fire it again when we get to Mars orbit. If we didn't fire in the second case, up here, if we didn't fire our engine to increase our velocity to match that of Mars, we would continue moving on the blue curve. In other words, we would follow the rest of the Hohmann transfer back to where we started in Earth orbit. But bear in mind, there is a problem. You might say to yourself, well, that's handy, because if we're on the blue Hohmann transfer, if we get to Mars and we decide for whatever reason we're not going to land on Mars, if we don't fire our rocket engine, then we simply come home again. Well, not quite, because it takes a year for the Earth to go around the Sun, and it takes about 2 years for Mars to go around the Sun. And when we calculate how long it takes to go on the blue Hohmann transfer, it's somewhere in between those, about a year and a half. That means if we follow the blue curve around and don't land on Mars and come back to Earth orbit, Earth isn't at that particular position anymore, because it takes about a year and a half to get back. And of course, it takes a year for the Earth to do a complete orbit. So in a year and a half, the Earth will have done 1.5 orbits, which means the Earth will now be at roughly this position where the cursor is. So the Earth won't be there anymore. Yes, we will come back to where we started, but the Earth has now moved. And so we can't get back to Earth by simply following the Hohmann transfer by not landing on Mars. This is one of the problems with getting to Mars and getting back again. It can only be done efficiently at certain times when Mars and Earth are in the right places in their orbits. So not only does it take something like a year and a half to get there and back, we also have to wait until Mars and Earth are in the right place in order to make a return journey. Hence, missions to Mars are years in length, not, for instance, missions to the Moon, which are only days or weeks long. And that poses quite a problem in terms of keeping the astronauts alive for many, many months, possibly years, on the way to Mars and on the way back, as well as their stay on Mars. What about other planets in the solar system? Well, in the 1960s, it was realized that if you fly a spacecraft close to another planet, it's possible to use it as a slingshot. A flyby of a planet can provide a so-called gravity assist and actually give you a higher velocity without you having to fire your rocket engine. That means you can take less fuel with you, which means you can take more scientific instruments with you. So that's great. Exploring the outer solar system thus becomes cheaper and faster. You have a higher velocity, so you get to your destination faster, and you need less fuel. So it's a cheaper mission. In effect, the spacecraft is robbing the planet of some of its momentum when it flies past. But how does it do that exactly? If we think about here on Earth, a ball rolling down a hill, let's imagine there's 2 hills and a valley between them. The ball rolls down the hill, and of course, as it rolls down the hill, it picks up speed. And its maximum speed will be in the valley, and then, assuming there's no friction, assuming there's no air resistance, the ball will roll up the other side of the hill, and if the second hill is the same height as the first, it'll end up at the same height where it started. But one thing we can actually calculate, or measure if we prefer, is what is the speed at a given height. And we find that the speed on the way down at a given height is exactly the same as the speed on the way up at the same height. In other words, regardless of where we put that horizontal grey line, it doesn't matter where we put the bar, if we were to measure the speed on the way into the valley, we find it's exactly the same as the speed on the way out of the valley. Whatever speed is gained by falling down the hill is lost on the other side going up the hill. It turns out it doesn't actually matter what the shape of the ground is. I've shown it as a symmetric pair of hills here. It doesn't matter what the shape actually is. The same principles apply. When you reach the same height, you will be at the same speed. So that seems to indicate that if we fall towards a planet and then pull away from a planet, whatever we gain on the way in, we'll lose on the way out. So how can a gravity assist actually work? If we think about coming into, let's say, Jupiter, we're not going to smash into Jupiter, we're just going to fly by Jupiter, and the closest approach to Jupiter should be the fastest speed that we will gain. So there's a particular speed on the way in and a particular speed on the way out, and if we go far enough away from Jupiter, those two speeds should be essentially the same from what we've just said about how gravity works. So if that's the case, how can we win? How can we actually gain something by flying past Jupiter? Well, the clever bit is the fact that the inward speed and the outward speed are both the same as seen by Jupiter. In other words, the origin of the gravity well. So as far as Jupiter is concerned, it's the same speed in and the same speed out. But Jupiter itself is moving around the Sun. So if we get the geometry right, if we arrange it so the inward speed and the outward speed are in different directions, and in particular, if the outward speed is in the same direction as Jupiter's motion itself, then the outward speed relative to Jupiter is still the same, but effectively the speed relative to the Sun can be essentially a lot higher than the speed relative to Jupiter, because we're gaining the Jupiter orbit around the Sun speed. And it can be quite substantial. For instance, we could have 10 kilometers per second as a speed heading towards Jupiter, but if we arrange it so that the outward speed is heading in the same direction as Jupiter's orbital motion, we might be traveling with respect to the Sun at perhaps 25 kilometers per second. So the speed relative to the Sun has gone up by a factor of, 2.5, simply by flying past Jupiter without using any fuel whatsoever. So that's how gravity assists can work in our favour. And that was done with Pioneer 10 back in the early 70s. A probe was sent from Earth, is shown in pink, and notice as it leaves Jupiter, as it will do in a few seconds, there it goes. Notice it heads off in a completely different direction and at a much higher speed. We'll see that once again in this particular animation. The spacecraft approaches Jupiter from one particular direction, but then the direction suddenly changes as it flies past Jupiter and it gains a substantial kick in velocity. In this case, fast enough to actually leave the solar system, even though it didn't have enough speed to do that initially. Pioneer 11 did something similar, but this time the spacecraft passed Jupiter and was given a sufficiently large kick to send it right across to the other side of the solar system. So notice where it first got the kick from Jupiter is on the opposite side of the Sun from where it eventually reaches Saturn. That's similar in many respects to the Hohmann transfer, where the Hohmann transfer from Earth to Mars occurs when Earth and Mars are on opposite sides of the solar system. The little tick marks you can see here are simply indicating that the path of the spacecraft are above the plane containing the orbit of Jupiter and the orbit of Saturn. So in this particular case, the probe was also given a kick as it went past Saturn, and you notice an abrupt change in angle and a change in speed. And again, Pioneer 11 will be leaving the solar system. The same trick was applied with the Voyager probes in the late 1970s. Initially, it was a probe that went to Jupiter, and Jupiter was then photographed and imaged, and then was gravity assist from Jupiter sent it on to Saturn. The principal reason for going to Saturn was to have a close look at Titan. Notice that as the spacecraft passes Saturn, there's no sign of a clear kick. It doesn't get a gravity assist from Saturn because they wanted the spacecraft to fly as close as possible to Titan, its moon, and the moon wasn't in the right position in order to get a gravity assist from Saturn. But given that Voyager 1 did exactly what they wanted, Voyager 2 was launched at approximately the same time, and it was also sent to Jupiter, but after being sent to Jupiter, it didn't have to go past Titan because that mission had already been achieved by Voyager 1. So after going past Jupiter, it was given a flyby of Saturn, which gave it enough of a kick to also do a flyby of Uranus and then Neptune. The idea of a grand tour that was predicted in the 1960s as a possibility because all the planets were lined up nicely for Jupiter, Saturn, Uranus and Neptune to be visited. So notice that after it gets a kick from Saturn, it gets another kick from Uranus, and when it passes Neptune, no particular kick. This is because when the space probe went past Neptune, they wanted to get a good look at as much of Neptune as possible. They actually flew over the North Pole and was given a little bit of a kick downwards. Again, there was no particular reason to have a gravity assist from Neptune. It was already going fast enough that they didn't want to bother about adjusting their position to get a gravity assist. What they were concerned about was getting the best possible images of the surface of Neptune and whatever moons they could. And again, these tick marks on the left simply indicate that after passing Neptune, the spacecraft actually took a dive below the plane of the orbits of the planets, the so-called ecliptic. If we have a look at the speed, let's take Voyager 2 as an example. If we look at its velocity as a function of its distance, velocity in kilometers per second, and distance measured in astronomical units, the distance from the Earth to the Sun, we see that it started with a velocity of about 35 kilometers per second. It very rapidly fell until it reached Jupiter, at which point it was given a kick, a gravity assist, and then again at Saturn, again at Uranus. And then notice that although it did increase its velocity as it passed Neptune, by the time it had finished going past Neptune, it was actually going a little bit slower than it actually approached. Again, this wasn't a gravity assist because it was simply, let's get the best possible images of Neptune. There was no particular impetus to get a gravity assist because it was already going fast enough. If we look at how fast do you need to go in order to leave the solar system, the escape velocity of the solar system, that's indicated by the blue line. So you notice that as it approached Jupiter, the spacecraft was not going fast enough to leave the solar system. And if it hadn't got a gravity assist from Jupiter, it would never leave the solar system. But as soon as it got that first gravity assist, which took its velocity quite high, then it's going fast enough and it's going above the escape velocity. And even though it then fell again as it approached Saturn, it's never from that point onwards fallen below the blue line. So again, it got another assist from Saturn, which gets it to Uranus rather faster, another little kick from Uranus to get it to Neptune rather faster, but it's already going substantially faster than necessary for it to leave the solar system. So all of these objects, Pioneer 10, 11, Voyager 1 and 2, because of gravity assists, they are all going to be leaving our solar system and hopefully passing nearby stars in perhaps 30 or 40,000 years' time. Now, gravity assists to help cover the enormous distances between the outer planets seems like a very sensible idea. But what's perhaps not so obvious is that gravity assists are also used to visit the inner planets. So for instance, Bepi Colombo, launched in 2018, will be going into orbit around Mercury in about 2025 or so. And you might think that's easy because you're falling into the inner solar system. But actually, you're falling in too fast. And what you really need is a flyby to lose speed. Otherwise, you would end up going past Mercury far too fast to be able to go into orbit. So Bepi Colombo actually did flybys of the Earth and multiple flybys of Venus, and it's already done a flyby of Mercury, each time with the geometry not quite like we saw with Jupiter, but a slightly different geometry such that the velocity of the planets it's flying by subtracts from its velocity. It slows it down. And a flyby, depending on the geometry, can either accelerate or decelerate your spacecraft, but the key observation is that in both cases you don't need to fire your rocket engine, so you save fuel. So your spacecraft is lighter, which means that you can have more scientific equipment on board. If we think about what happens when you get to your final destination, for instance, when Cassini went to Saturn to take images of the planet and the rings and various moons, they wanted to be able to look at Saturn from various angles. So they didn't simply go into orbit around Saturn and then stay put. They kept changing the orbit in order to get different views of the planet itself. And you can see just how complex the orbital structure was and how often it changed by looking at this 3D picture of just what Cassini was doing over a period of quite a few years. Every time you want to change orbit, you have to fire some rocket engine. You have to use a little bit of fuel to change your orbit from one shape to a different shape, or from one size to a different size. So you might use gravity assists to get you to your final target, but you'll then need to use a little bit of fuel in order to change what you do when you arrive, if you have a certain scientific mission. Let's finish by thinking about these ideas of parking places. What are these Lagrange points all about? Well, let's go back to the original key observation that if we've got a couple of planets going around the Sun, then the object that's closer to the Sun feels a stronger gravitational pull, so moves faster. So for instance, if this was the Earth and Mars, the Earth would be going around the Sun with a shorter period than the length of time it takes Mars to go around the Sun. And that's important enough to run the animation twice, because this is key to what I'm about to say. Generally speaking, closer to the Sun means faster and hence shorter orbital periods. But then you can ask the question, does it always have to be that way? If we think about the pull on the red object and the pull on the green object, they're shown by those two arrows. Because the green object is closer to the Sun, it's got a slightly larger arrow because it's got a stronger pull to the Sun. And we can ask ourselves, well, will that always be the case? Well, certainly you can't change the gravitational pull of the Sun for any given object. But what you can do is arrange it so an object, let's say the object in the red orbit, feels an additional gravitational force. So let's imagine that green represents the Earth, so the Earth is going around the Sun in exactly 1 year. The red orbit has a period of more than 1 year, because if you ignore everything else, the red object is being pulled with a smaller gravitational force. So it moves more slowly, it takes more than a year to go around the Sun. But what if the red object is close enough to the Earth so that it's being pulled not only towards the Sun, but being pulled towards the Earth as well? In other words, there are now two gravitational forces on the red object. It's being pulled towards the Sun and it's being pulled towards the Earth. And as long as the red object is close enough to the Earth, we can arrange it so that extra pull from the Earth makes the difference. It makes just enough difference to ensure that the red object goes round the Sun not in more than a year, but in precisely 1 year. What does that mean? That means the red object now stays in sync with the green object, the Earth. Notice that the red object is being pulled towards the Sun, and the pull of the Earth is always in the same direction. They are always adding together, and so they will always stay in sync. And again, let's just run that animation again. So that means, as seen from the Earth, the red object always seems to be in the same place on the opposite side of the Sun. The sun and the earth and the object are always in a straight line. And that is the essence of what Lagrange points are all about. If we have a look at the right-hand side of this diagram, the point we've just been describing is what can be described mathematically as Lagrange point 2, or L2 for short. Because anything that's at L2 is being pulled towards the sun and the earth, and hence goes round in 1 year. Note that this is not to scale, because the distance from the Earth to the Sun is 1 astronomical unit by definition, and the distance from L2 to the Earth is only about 1% of that. So this diagram quite definitely not to scale. I've exaggerated the scales simply to make it easier to see what's going on. So the distance from L2 to the Earth, given that 1 astronomical unit is about 150 million kilometres, the distance from L2 to the Earth is about 1.5 million kilometres, or about 1 million miles. And given that this side of the Earth is where we define noon, midday, and this side of the Earth is where we define midnight, away from the sun, you could say that L2 is simply hovering 1 million miles above midnight. That's why when some people talk about the James Webb Space Telescope, which is parked at L2, it is hovering above the Earth 1 million miles above midnight. L1 is conceptually similar. It's another Lagrange point, but this time the pull of the Sun and the pull of the Earth are in opposite directions, and instead of the orbit of L1 being less than a year, those pull of Earth and Sun in opposite directions keeps L1 going around the Sun again in exactly 1 year. And again, the distances involved, Earth-Sun is 1 astronomical unit. The distance from L1 to the Earth is very similar to the distance from L2 to the Earth. It's about 1% of that distance. L1 is an ideal place to put a spacecraft for observing the Sun. Because if you want to observe the Sun, you don't want the Earth to get in the way, and L1 has an unobstructed view of the Sun because it's always on the line between the Sun and the Earth. There are actually 5 Lagrange points for any given system. So for the Earth rotating around the Sun, there are 5 Lagrange points. For Jupiter going round the Sun, there are also 5 Lagrange points. And here they are marked. I'm not going to talk about all of them. We've mentioned L2 and L1. L2 is a place that's very useful for putting spacecraft because, for instance, a sun shield on the spacecraft can be aligned such that it blocks the light from the Sun and the Earth and the Moon without changing the position of the sun shield. For any other spacecraft in any other position, the Earth and the Moon and the Sun will be in different directions of the sky, and you can't have a single shield block all of the light from all of those objects. So there are spacecraft such as Gaia and the James Webb Space Telescope which are located at L2 as it's a convenient place to block light from these objects. Actually, L2 itself is a point in space which is actually in the Earth's shadow. So if you want to use solar panels to keep your spacecraft powered, you don't sit actually at L2, you put yourself in a little orbit around L2 to keep yourself out of the Earth's shadow. And the reason that L2 is so useful is because it's effectively a parking space. If you imagine the spacecraft, if we take L2 there, if the spacecraft happens to drift in the direction I'm showing by my cursor, then the Earth tends to pull it back again. And if it drifts in this direction, the Earth tends to pull it back again. So those 2 green arrows show that the position of the spacecraft is, in a sense, self-correcting. If it drifts away from L2, the Earth pulls it back again. So that's why we think of it as a parking place. That's not strictly true, because if we think about the opposite direction of drift, what if the object were to drift towards the Earth or away from the Earth? Well, any drift in those directions doesn't get self-corrected. So we do need to keep a little bit of fuel on board our spacecraft such that if it drifts towards or away from the Earth, we can in principle give it just the smallest of nudges to keep it at L2. But unlike other objects in the solar system, we don't have to continue continually use fuel to keep it in the same position relative to the Earth. Just a little bit of occasional station keeping. And we can see that in this rather colourful way of visualising how to stay in either L1 or L2. The ability of a spacecraft to park at a particular point can be visualised using this particular graphic here. Imagine that these coloured contours represent, for instance, height above sea level, and think about a ball that wants to roll downhill. If we have a look at these contours, in particular if we look more closely around L2, so let's blow that red rectangle up a little bit so we can see what's going on. Downhill, as far as these contours are concerned, are in the directions of the red arrow. In other words, if we were to drift away from the L2 point, downhill pulls us back again. If we were to drift in the other direction, downhill pulls us back again. But if we were to drift to the left towards Earth, we would keep going downhill. If we were to drift to the right, we would keep drifting to the right, downhill again. So this particular point in space is not a hilltop as seen by these contours. And it's not a well, because in two directions we are always being pulled back again, but in two other directions we're not. So it's not the top of a hill, and it's not the bottom of a well. It's actually a so-called saddle point, because if we were to think about the contours immediately around that particular point in space, it looks like a saddle. In two directions it goes up, and in two directions it goes down. So a take-home message for this is, if you want to park a spacecraft, one way of doing it is to send it to the L2 point, which is a Pringle. So the Gaia space probe and the James Webb Space Telescopes are both sitting at a Pringle in space. Okay, strictly orbiting around a Pringle, same idea. And because a slow drift towards Earth will need the occasional nudge, then the James Webb Space Telescope and Gaia will need to expend a little bit of fuel. Every few months they'll just need the smallest of nudges just to stop them drifting towards the Earth. But they don't need to keep firing their rocket engines to keep them in the same position relative to Earth. Just an occasional nudge every few months. So these Lagrange points can be extremely useful for parking spacecraft. Let me finish just by saying that not all orbits behave the way we expect. We like to think of orbits as being circles or possibly ellipses. But in fact, it is possible to have orbits. Remember, an orbit is not a closed loop necessarily, it's just a motion of an object under the influence of gravity. If we took three objects, these three coloured here, red, green and blue, and we place them in just the right place, and then allow them to attract each other through gravity, blue will be pulled downwards because red and green are both below it, red will be pulled to the right, and green will be pulled to the left. But what paths will they follow? It is by no means obvious what will happen unless we run a simulation, and the results are very surprising. This is what actually happens. Those three objects are simply moving under the influence of gravity of the other two objects. They stop and then they fall back and follow exactly the same paths in reverse. And they will simply do that back and forth and back and forth. If nothing gets in their way, they will continue to move back and forth along those red, green and blue paths. Now that's really weird, and you could ask yourself, is it possible for any three objects to actually do that? For instance, if we have a triple star of three stars of equal mass, could you possibly get them to do that? Well, the answer is no, because you could never get them in the right place under the right starting conditions to allow them to start where I've shown those three masses and then follow them in this particular way. In other words, when stars are born, they're always in motion, and we can never have the right starting conditions. We can never have the right initial conditions to start moving in this way. So it's a mathematical solution of how three bodies would move, but it's not of any practical significance. And if we're talking about orbits, Well, don't get me started about black holes. Around a black hole, space is so distorted, so warped by the presence of the black hole, that we can't even think of closed loops. We can't even contemplate circles, ellipses and parabola anymore. Newton's laws no longer apply, and we get weird and wonderful loops of objects orbiting around black holes. Again, this is not something we have to worry about if we're putting satellites in orbit around the Earth. It's just a bit of a curiosity. So why is rocket science considered to be so hard? Putting rocket technology and rocket engineering to one side, whenever we think about rocket science and how to get from one planet to another, it's considered to be very, very, very hard. Well, yes, it's true that there are some objects in the solar system that move in ways that are not, at first sight, in any way intuitive, and it takes a little bit of figuring out how they're actually moving. Even though the underlying physics is straightforward, two objects attract each other via the gravitational force. And indeed, calculating how to put the James Webb Space Telescope into orbit around L2 last year was not a trivial feat, especially given the phenomenal accuracy they actually achieved in getting the James Webb to where they wanted it to be in such a way that they used so little fuel that its mission parameters have now been extended from nominally 5 years, perhaps out to as long as 20 years because of that fuel saving. But despite the fact that actually achieving these things is incredible, the underlying idea, the underlying concept behind rocket science is straightforward enough. In any situation, if you have stronger gravitational pull, that will lead to faster motion. And the simplest way of remembering that is just to remember that the Earth goes round the Sun faster than Mars goes round the Sun, simply because the Earth is closer to the Sun. And that, in a sense, is really all there is to it. Everything else is just maths. After all, it's not rocket science. Thank you for listening.